very technical talk, so forewarning. This talk basically comes up from all my tinkering around with exploit writing, with shellcode writing, with ARM assembly, and then my personal vendetta against how signatures, rules, and updates are the only three ways that people know how to do InfoSec defense. So it ends up being one of my personal goals to defeat any signature mechanisms, not because I want to do evil things, but because I just want to make boxes with blinking lights useless. Right, so my name is Saumil. I've been doing InfoSec for a very long time. Let me skip the introduction and get straight to the agenda. A little bit of background. When we're talking about shellcode, these days most of the research out there in the public is x86 shellcode. There's a little bit of ARM shellcoding out there. For the two of you who suffered my class for the past 3 days, you've written ARM shellcode from the ground up. And that's fine, it's good, but ARM shellcode is still in its nascency. It's largely published on a few sites. Simple shellcode exists out there. And I thought to myself, okay, let's take ARM shellcode a step further. So I was working on 3 projects, out of which one project got solved really trivially, so I'm not going to present that trivial stuff on how to solve cache coherency issues. We will instead talk about 2 types of R&D that I've done with ARM shellcode. One is whenever you're trying to inject shellcode and you have space limitations. How do you get around tight spaces? How do you get around confined spaces? And in the x86 world, most of us are familiar with the egg hunting technique. Your shellcode itself lives completely in a different memory area, but you inject a very small search and destroy routine called an egg hunter, which scans your entire process for the presence of the larger shellcode, jumps to it, and executes it. So again, nothing new as far as egg hunting goes, but I made a few modifications to the egg hunter, which I will talk about. But then most of the talk is going to be focused on polyglot tricks with ARM shellcode. I also like polyglot techniques very much. And polyglot techniques is where the same data carries 2 completely different meanings when viewed in completely different context. One of my research areas with polyglots was stegosploit, which got more misunderstood than it was understood, was about how to deliver browser exploits encoded as pixels on a picture. So if you view the data in a JPEG viewer, it looks like pure pixels. So on a browser, it just shows you an image. But if you treat the data as JavaScript, then it actually executes in the browser. That's a polyglot. The ARM polyglot is not as cool as that one, but it's still a polyglot. And then, of course, there's demos. So without further ado, let me just give you a very brief context about ARM and ARM assembly and ARM shellcode in exactly 59 seconds. ARM is a RISC processor. ARM has 2 instruction sets overlaid into it. There is what we call as the 32-bit instruction set called the ARM instruction set. All instructions are fixed width. And then there is a subset of most popular instructions available as thumb instructions, where a thumb is much smaller than an arm. Well, actually, in the case of ARM, a thumb is half the size of ARM, which is quite kind of weird, but it is what it is. So thumb instructions are more compact, and shellcode writers prefer to write all their shellcode in thumb because shellcode has to be compact and shellcode has to be free of bad characters and whatever have you. However, whenever you're writing ARM shellcode, if you're a shellcode developer, the first thing you want to do is you'll always start out in ARM mode. That is, all your instructions initially will be decoded as 32 bits. You want to switch over to thumb mode very quickly, as soon as possible. So you do something called what's called an ARM to thumb switch. That one. My laser pointer is weak. So the blue text is the ARM to thumb switch. These are 2 32-bit instructions which will immediately flip you over to thumb mode, and the green instructions are all thumb. as you can see from the disassembly, and the shellcode executes. This one is basically launching you bin shell. So with this little background, I'm going to give you the two demos. First, I'm going to give you the egg hunter demo, where we will load the shellcode in random areas of the process, like the heap, and then the egg hunter will come searching around, find it, trigger it, and launch a shell. There are some complexities. Because it's 2018, we now have exploit mitigation technologies available, called data execution prevention is one of them, where the data in the stack and the heap is not executable. So therefore, we basically need to do some memory protection techniques, and that's where this research comes in. Okay, so let me set the context for the egg hunter. What happens if basically your payload exceeds the size constraints? In this example, you have a stack overflow. A local buffer has very limited space, and the programmer hasn't coded it properly, as usual. Blame the programmer for everything. That's why we have jobs in InfoSec. So you're going to attack it. You're going to overflow this thing. You're going to put in your ROP chain. The ROP chain will basically do the fancy stuff and bypass data execution prevention, making the stack executable. And then you have your shellcode. But what happens if the shellcode is too long? There are several conditions. Sometimes you might overwrite a local pointer in the local variable space. And the pointer is executed or dereference, it causes a seg fault. If you hit the bottom of the stack, you may hit a seg fault. So if space is a limitation, we have solutions like the egg hunter. So what does the egg hunter do? Basically, the egg hunter, like I mentioned, it searches for an egg in the process memory layout. The egg is nothing but a 4-byte value, but then it searches for 2 consecutive occurrences of the egg, because sometimes you may have that 4-byte value occurring somewhere else, and that's a false positive. So the egg hunter is a shellcode which keeps on going page after page after page, looking to see if you have 2 instances of the string somewhere, followed by real shellcode. When it finds it, it jumps to that real shellcode, and that's the end of it. It's a generic technique. The way the egg hunter works is essentially the egg hunter uses syscalls to determine whether memory pages exist or not. So you're traversing through process virtual memory, go page after page after page. All of a sudden, you land into an unmapped memory region. If you try and dereference it in user land, you're going to seg for your own self, which isn't cool. So you do a syscall to see if the page exists or not, using some innocent syscall, which returns you either E, no mem, or success. And then once you find the page, you scan it, see if the egg's there, and then transfer control. Now, the egg hunter is nothing new. I mean, there's nothing radically new about the egg hunter. This has been done before. But the problem exists with data execution prevention. That's what I'm going to talk to you about. So I'm going to give you the egg hunter demo. First, I'm going to explain this thing with pictures, what I just said in words. You have the process memory layout over here. You have the binary, the heap, stack, and everything. You have the shellcode preloaded in the heap somehow, through some input or whatever have you. You've injected the shellcode in the heap. You don't know where it is, but it's living in the heap. And the 2 pink words which say hack, hack, that is the egg, the string of your choice, and then the shellcode that follows it. Now, when you have your stack overflow, you stuff in your ROP chain. The ROP chain will basically turn the memory of the stack, read, write, and execute. And then, after the ROP chain, you basically jump to the egg hunter shellcode, which is what I'm going to present. The egg hunter is going to travel through the memory space, searching for the string hack, hack, 1 page at a time. So it's going to keep on looking. If it hits the bottom, it's going to wrap around at the top and scan these pages until it does find 2 occurrences of the string. And then it's going to jump to it. The problem is the heap is not executable. Right? So this is where it's going to fail. And you're going to run into a problem. So with this, let me give you a very quick demo of the egg hunter and how it's laid out. There. Can you folks all read this stuff? Okay, great, excellent. Cheat sheets. So I have a simple program with a vulnerability. And here's your classic vulnerability. You have a string copy in a buffer, and you overflow the buffer with more than 128. You get a buffer overflow, you get shellcode. Here's the shellcode. Right now, the shellcode is basically breakpoint instructions. And because this is a toy example, I'm just loading it in the heap myself, suffixed after these two hack signs. In the shellcode, I'm going to inject the egg hunter and then show you how this whole game goes. Right. So let me load this in the debugger. If I run a regular buffer overflow, like I just give it a very large string, it's going to crash, and there it is. You're going to get a segmentation fault. We control the program counter, all that fun stuff. If we search the memory space of this process, your heap is at, in this case, at address 11,000. Your stack's over here. Both of them are non-executable, as they should be. And if I search the heap, this is a problem of live demos. Like you have to type out everything pretty fast. Okay. So I'm going to search the heap for the string hack if it occurs in the heap, and sure enough, it occurs at 2 locations. I'm going to dump the string over at the first location. And yeah, this is where it is. This is the egg hack, and this is the rest of the shellcode. Right now, the page permission for this address, if I look at it, is the page permission is just read and write. So even if we jump to it, it's going to fail. Okay. Let me now show you the egg hunter code. And this is where the mprotect egg hunter enters. This is the modifications that I made to the egg hunter. So this is basically a generic egg hunting shellcode. I mentioned to you the whole process of searching for the memory pages, whether they exist or not. I just did a very simple trick. Instead of searching for the pages using any other random syscall, I will search the pages using the mprotect syscall itself. So as I go searching the pages, I'm going to mark the pages executable as we go along. So basically, this is what we're going to do. The mprotect egg hunter, the moment you invoke it, it's going to search the memory pages, and as it goes, it's going to mark them RWX when it finds a valid one. So by the time we reach the heap, the page is already RWX, and our shellcode is ready to be executed. And this is the demo that I'm going to give you. Right. So the mprotect egg hunter is already in place. I'm going to run this program again with the exploit which has the egg hunter attached to it. Now when I run it, the exploit is right now just triggered to stop at a program counter. And if I look at the memory map, right now the stack is executable. The heap is still not executable. So this is basically the same exploit with the ROP chain. Now after the ROP chain, I'm going to invoke the egg hunter, and now that I do this final, notice that instead of landing, instead of my program counter crashing, my program counter ended up in the heap at the breakpoint instructions which I've placed in the shellcode. These two highlighted areas are the words hack. program counter is at 11,000 hex 10. And if I now look at the VM map, the egg hunter went and painted all these pages RWX. So now the heap is RWX, shellcode can execute. And I will give you the final demo with egg victim 1, where we have real shellcode loaded in the heap, which is going to launch you bin shell. And if I run the final attack that I did just previously, instead of the breakpoints, this should drop us into a shell, which it does. It doesn't crash on us. Right. So this was just the this was just a demo on about the egg hunter and the exploit that contains egg hunting. This could be applied to any ARM exploit. Wherever you have space limitations, go ahead, do the egg hunting. Okay, now next one. Next, we're going to talk about the polyglot shellcode and where does the polyglot shellcode come in. And this also brings me to my whole discussion on signature-based defenses. Several people pointed out whenever I teach ARM shellcoding, they say, oh, hey, but we can always write a signature for this. We can detect the ARM to thumb switch, and this is going to be very much the same with every shellcode. So if we see an ARM to thumb switch with some thumb instructions, we're going to flag it bad, saying that, and then all your bro, Yara, IPSs are going to start screaming, and then all the DFIR folks are going to start jumping around. But that's all classic bullshit. So I said I have to put an end to this signature thing, like once and for all. Not by just bypassing a signature, but coming up with an entire different class of shellcoding, which cannot really be signatured tractably. And then I also came to know that in several embedded situations, this is a nice side benefit of the polyglot. There are some processors which do not implement the ARM instruction set. They are thumb-only processors. All the Cortex-M processors, the microcontroller processors, they don't have the ARM instruction set. So I have basically ended up creating this one shellcode which can run in ARM mode and switch you to thumb, or the same piece of data can be a polyglot. If you force it to run in thumb mode, it literally passes through and keeps you in thumb mode. The instructions are basically chosen. The same instructions do different things in ARM and thumb. So if you start in ARM mode, the instructions will leap you to thumb mode. This word quantum leap was coined by a student at 44Con in September. I like that term, so I now, instead of calling it universal mode shellcode, which is nice, quantum leap sounds cooler. So you have to have the right nomenclature, otherwise people don't pay attention to you in InfoSec. Or you have to have a right logo, something like that. Anyway, so if you start in ARM mode, the quantum leap instructions will switch you over to thumb mode. But if you start in thumb mode, these same instructions will literally just pass through and do nothing, keep you in thumb mode. And byte by byte, these instructions are exactly the same. So the starting mode of the processor, the shellcode switch part is agnostic to the starting mode of the processor. Now, how do you cook all of this stuff up? To do this, you kind of have to have a warped mind to think in terms of polyglots. But most importantly, you need to be able to understand ARM and thumb instruction encoding very, very well. And playing around with RISC processors, instruction encoding in RISC processors is a science, but it's actually also an art. It basically depends upon how clever can the engineers be to pack as much information in a single bit as possible. So we want to choose instructions which will do something meaningful when run in ARM mode, but the same ARM instruction, it is 4 bytes long. You split an ARM instruction into 2 thumb instructions. Each of these thumb instructions simply does nothing, lets you pass through. To understand this, we also will talk about conditional execution in ARM, which is really useful, and that's what makes the polyglot support happen. And then we need some luck and perseverance. Okay, so kind of going to get you to the ARM to thumb switch. If we take this blue code, which is the ARM to thumb shellcode switch code, and forcibly convert these 8 bytes of ARM instructions into, forcibly convert these 2 ARM instructions into 4 thumb instructions. This is what the conversion looks like. So byte by byte, the first add instruction becomes an arithmetic shift right and a branch instruction. And then the second branch instruction in ARM becomes a, I don't know what the hell this opcode means. I just call it very horrible add instruction. It's like a vector floating point instruction, which I have no idea what it does, right? But basically, I don't want that. So now when you're doing this polyglot stuff, you want the good instructions to stay through. This one's a good instruction. The ASRS, arithmetic shift right, no problem. I can live with that. Doesn't destroy me. But the destructive ones are the branch instructions. They'll transfer my program control, screw me up. Can't have a branch. This vector horrible instruction, I don't want that either, because I don't know what it does. And then I also wanted some better goals for myself, that this should work on the lowest common denominators of ARM, the ARMv6 or ARMv5. We don't need special thumb instructions. We don't need illegal instructions. So with these objectives, I started playing around with ARM and thumb decoding. If we take the first add instruction, the add PC,1 is basically responsible for setting the thumb flag, and then the branch will switch to thumb. If we take that add instruction and decode it bit by bit, all the 4 bytes decoded, every ARM instruction always has fixed areas. Like the first 4 bits will be the conditional bits, then immediate, opcode, status, first operand, destination register, and second operand. This is, the format of decoding is fixed. Now, if we take the least significant 16 bits, that is the first thumb instruction, now we're going to split that and view them as 2 thumbs. And the most significant 16 bits are the second thumb instruction. What will influence each of these thumb instructions? So the first thumb instruction, the instruction itself is controlled largely by the destination register, that is the R1 over here, and the operands of the ARM instruction. The second half of the ARM instruction controls this instruction. It's easier to control because you can choose what to put in there. The first, the second thumb instruction is basically controlled largely by the opcode and conditional flags. This is tricky, because if you want to do an add, then you only get a limited few choices of thumb instructions which the add will translate into, and that's what screws us up. Fortunately for us, we have the conditionals to help us out. So if I do the decoding, the second thumb, the second half, the first thumb instruction is easy, that results into ASRS, and it is this R1 in the ARM operands that is responsible for the choice of opcode in the thumb mode. In the second instruction, the opcode is influenced by the conditional flags, which means that I have to now, if I want the valid decoding to happen in the thumb mode, and I don't want the branch instruction, if I want to change the branch, I have to play around with conditional flags. Now, in ARM mode, any instruction can be made conditional. That is, instead of add, you can have an instruction variation like add if equals, add if not equals, add if greater than, add if not greater than, something like this. But if an ARM instruction is made conditional, we don't have any guarantee of it executing. What if the conditional situation is different and it doesn't execute? Then that screws us up. So how can we make ARM instructions conditional, yet execute them unconditionally? Force them to be executed unconditionally. And the guarantee is made by using complementary conditions. So instead of one instruction, add, you always place 2 instructions, but the conditional flags are complementary. The first one is add if not equals. Okay, if that doesn't go through, the second one is add if equals. One of them is bound to go through no matter what the conditions are. But by adding the conditional flags, I have changed the first 4 bits of the resultant encoding. Now, if I do the decoding, things look a lot better. So the first instruction is add if not equals. I decode it. Okay, the first ARM instruction is still ASRS, that's okay. The second thumb instruction is now based on the not equals condition in the first instruction. And that also results in an ASRS, which is fine. Then if we go to the second one, again an ASRS, and then the next condition equals results in LSLS. By playing around with conditions correctly, I can therefore control what instructions will be generated when viewed in thumb mode. And in this case, all the instructions are okay, and I'm not bothered or not limited with any of these issues. No destructive instructions. So with this theory, how to come up with the final shellcode? Let me show you. Just a sec. So I made one iteration. Basically, you have to add some odd number to the program counter and branch. That is what's going to switch you into thumb mode. So my first attempt, I made several attempts, as you can plainly see from all this. I'm not going to go into each and every micro detail of the attempts. But let me show you a good attempt that succeeded. Not succeeded, sorry. Cat universal mode 2. So I tried the first one was rather simple. I just did 2 adds with complementary conditions, and then instead of a branch, I did a move PC, R1. This had promise, but it didn't do well when I force decoded this into thumb. So then I went, instead of then I started playing with a choice of registers. Instead of R1, I started playing around with R4. R4 started giving better choices. So if I do the object dump with in ARM mode, the object dump in ARM mode is normal. This is how it's supposed to be. And if I force the object dump into thumb mode, then you notice that the thumb mode, this stuff is kind of okay, add, move, and no problem. These 2 instructions are valid instructions, but they are thumb 2 instructions. It is only worked for ARM v7, the newer cores. ARM v6 cores don't support thumb 2. So while this code will work, I wasn't very happy with it. I want pure code which works in the lowest common denominators. And this basically leads us to the final iteration of the code. This is the final shellcode that I created. This is the switch. You do the add, you then basically save the stack pointer, you push the register, you push this destination register on the stack and pop it into the program counter. So instead of the branch, I did a push and pop, push on the stack and pop into program counter. And this avoids any destructive instructions. This basically took like 4 nights of work. You can only work at night because then you get 8 hours of uninterrupted time. You're wrecked during the day, but it's good output. So 4 nights have gone into this, but now you can see the resultant instructions are all non-destructive. You have add, move, compare, nothing wrong with this. So now let me give you the demo. I have 2 demos. One is if I start in ARM mode, I should switch to thumb mode. So I have the test in ARM mode. I'm going to start in ARM mode. This is the quantum leap stub, which will switch me to thumb mode, and the rest of the shellcode is in thumb. This should work seamlessly. And the second demo is if I start in thumb mode, then I should stay in thumb mode. So this is the thumb test. well, my processor right now is an ARM processor. So first I will switch it to thumb. Then here is the quantum leap code in thumb, which should stay in thumb and still execute the shell. So first debug demo. Right. Load it up. I hope this works. Yeah, otherwise I look like a fool, right? Who is a greater fool? We'll have to debate about it. Okay, me for screwing up or you for having me here? Anyways, so here we are. Right now you're in ARM mode. Basically, the debugger tells you the thumb flag is off, so you're in ARM mode, and the program counter is going to start. This is the quantum leap stub. It's going to execute these instructions. Let me dump out these instructions. So these are the instructions that the program counter is going to execute, and then after that, you have thumb instructions. So I'm going to step through these instructions, step through all 8 straight away. And now this quantum leap code is done. Let's check the mode. Wow, now we've been placed into thumb mode. So the switch happened, and the rest of the shell code is in thumb. If I continue, I'll get a shell, and this is working. So if you start in ARM, you switch to thumb, and then things work. Now, the last one. If you start in thumb, then you should stay in thumb. The instructions shouldn't destroy you, and that's the last demo coming up. Start it. So first I will forcibly switch to thumb mode before doing the quantum leap code. So I'll step 2 instructions, which now have switched me into thumb mode. So we'll consider this as the starting point. If I now dump the instructions in ARM, this is the quantum leap shellcode when viewed in ARM mode. If I view the same instructions in thumb mode, 8 instructions result into 16 thumb instructions, and these are the same instructions when viewed in thumb mode. Now I'm in thumb mode, so I'm going to basically step through all 16 of these, and the end result is I should stay in thumb mode. So I step through all 16, I'm still in thumb mode, and then if I continue forward, I get my shell again. So basically what's now done with this quantum leap code, this polyglot stunt, is, okay, not only have I achieved mode independence, but there's no way you can signature a polyglot like this. Yeah, good luck writing those Yara rules. And if you do write a clumsy Yara rule which matches this, then I will change the conditionals, I will change the registers and mutate this. Probably I can create like damn nearly endless mutations and change the order, and you will not be able to write any regular expression. Then of course, then what you do is you throw machine learning at it, because that's going to solve everything. But anyway, by that time happens, I'm sure we'll put out another talk and another polyglot to beat the shit out of that as well. Right, so the final stuff in the quantum leap code, this basically worked. I did the demo, conclusion. So there's a lot of opportunity, not only for exploring ARM shellcode, but also explore tricks with ARM shellcode. These are just 2 tricks that I presented. If you want to play with them, the code's available on GitHub. Take it, modify it. If you find better tricks, please let me know. I'll buy you beers and or any beverage of a choice. And then that's about it. Thank you very much for your time and attention.